Have you ever wondered how self-driving cars navigate busy streets? Or how your phone understands your voice commands? The answer, my friend, lies in the fascinating world of machine learning. It's a field where computers learn from data to make decisions, predictions, and even, sometimes art. Think of it as giving computers a brain that gets smarter over time. Of course, there are many ways to teach a computer, and today, we're diving into one of the most popular and powerful methods: supervised learning. Supervised learning is like teaching a child with flashcards. We show the computer labeled examples, it learns the patterns, and then it can recognize new unseen examples. It's the driving force behind many AI technologies you interact with daily, often without even realizing it. From personalized recommendations on Netflix to spam filters in your inbox, supervised learning is quietly working its magic behind the scenes. But before we get lost in the technical jargon, let's break down what supervised learning really means in a way that everyone can understand. We'll explore how it works, its real-world applications, and even its limitations. So buckle up and get ready for a crash course in one of the most transformative technologies of our time. By the end of this journey, you'll not only grasp the fundamentals of supervised learning but also gain a newfound appreciation for the incredible ways it's shaping our world. Let's begin, shall we? Imagine you're teaching a child to identify different fruits. You show them a picture of an apple and say, "This is an apple." You repeat this process with pictures of bananas, oranges, and grapes. Each time, you provide the correct label, helping the child learn to associate the image with the right word. That, in essence, is the core principle behind supervised learning. In supervised learning, we feed the computer with labeled data. This data consists of input features, like images of fruits, and their corresponding labels, like apple, banana, or orange. The computer then uses this labeled data to train a model, which is basically a set of algorithms that can learn to map the input features to the correct labels. Think of the model as a student trying to learn the relationship between the pictures and the fruit names. The more labeled examples we provide, the better the model becomes at recognizing the patterns and making accurate predictions. It's like giving the student more flashcards to practice with. The goal is to train the model to a point where it can accurately predict the label of a new unseen example, such as identifying a picture of a pear as pear, even though it wasn't part of the initial training data. This ability to generalize from known examples to unknown ones is what makes supervised learning so powerful and widely applicable. It's the foundation for a wide range of AI applications, from image recognition and natural language processing to spam detection and medical diagnosis. Let's dive a little deeper into the flashcard analogy to understand the key components of supervised learning. Imagine you have a stack of flashcards. Each card has a picture of an animal on one side, and the animal's name on the other. This stack of flashcards represents your labeled data. The pictures of animals are the input features, the information the model will use to learn. The animal names are the labels, the correct answers you want the model to predict. The process of showing these flashcards to the computer and telling it the correct animal name for each picture is called training. During training, the model tries to find patterns in the input features that correspond to the labels. For example, it might learn that pictures with pointy ears and a bushy tail are often labeled fox, while pictures with stripes and a mane are usually labeled zebra. The model uses these learned patterns to create a set of rules, or a mathematical function, that it can then use to make predictions on new, unseen data. Once the model is trained, you can test it by showing it a new picture of an animal it has never seen before. The model will then use its learned rules to predict the animal's name. If the model has learned well, it will predict the correct name with high accuracy. This is how supervised learning enables machines to learn from examples and make intelligent decisions. Supervised learning isn't just a cool concept. It's the engine driving a revolution in how we live, work, and interact with the world. From the moment your alarm clock powered by sleep cycle analysis wakes you up to the facial recognition that unlocks your phone, supervised learning is subtly woven into the fabric of our daily lives, but its impact extends far beyond convenience. In healthcare, supervised learning algorithms are being used to diagnose diseases like cancer earlier and more accurately, potentially saving countless lives. In finance, it's helping to detect fraudulent transactions, safeguarding our economic systems. And in environmental science, it's being deployed to analyze climate patterns and develop strategies to combat climate change. The possibilities with supervised learning are seemingly endless. As we feed computers more data and refine their learning algorithms, they become capable of solving increasingly complex problems that were once thought to be the exclusive domain of human intelligence. However, it's important to remember that supervised learning is not a silver bullet. It has its limitations, which we'll explore later. But for now, let's delve deeper into the fascinating world of supervised learning and uncover the mechanisms that make it all possible. In the next section, we'll unravel the step-by-step process of how machines learn from data. Get ready to unlock the secrets behind this game-changing technology. Just like we need food to fuel our bodies, machines need data to fuel their learning. In supervised learning, this data comes in the form of labeled examples, providing the machine with both the question and the answer. Think of it as creating a giant study guide for the computer, filled with examples and explanations. The quality and quantity of this data are, well, absolutely crucial. Imagine trying to learn a new language from a textbook with only a handful of words and sentences. You wouldn't get very far, would you? Similarly, a machine learning model trained on a small or biased dataset will struggle to make accurate predictions. It's like trying to understand the entire world based on a limited and potentially skewed perspective. The type of data used also depends on the task at hand. For image recognition, the data might be millions of labeled images, while for predicting customer churn, it might be customer purchase history and demographic information. The key is to select data that is relevant to the problem you're trying to solve and representative of the real-world scenarios the model will encounter. Gathering and preparing this data is often the most time-consuming part of the supervised learning process. But it's a crucial step. As the saying goes, garbage in, garbage out. If you train a model with bad data, you'll get bad results. So, feeding the machine a healthy and balanced diet of data is essential for success in supervised learning. Now that we have our data, it's time to give it meaning. This is where labeling comes in. Labeling is the process of assigning a meaningful tag or category to each data point. Remember our fruit example? Labeling would be like putting a sticker on each picture that says apple, banana, orange, and so on. This labeling process is what makes the data understandable for the machine. It's like providing a translation for the computer, converting raw data into a format it can learn from. Without labels, the machine would just see a bunch of pixels or numbers, without any context or meaning. Labeling can be done manually, which is time-consuming but often more accurate, or automatically, using algorithms to assign labels based on certain rules or patterns. For example, in spam detection, emails can be automatically labeled as spam or not spam based on keywords, sender information, and other factors. The accuracy of labels is paramount. Imagine a mischievous friend sneaking into your fruit labeling session and randomly swapping some labels. The machine would learn the wrong associations and make incorrect predictions. This is why data quality and accurate labeling are critical for the success of any supervised learning model. It's all about setting the machine up for success with clear, consistent, and accurate information. With our labeled data ready, it's time for the machine to hit the books, or in this case, the training data. During training, the labeled data is fed into a chosen algorithm, and the algorithm's job is to find patterns and relationships between the input features and the labels. Think of the algorithm as a detective trying to solve a case. The detective carefully examines the evidence, our data, and looks for clues, or patterns, that connect the suspect, which is the input features, to the crime or the label. The more evidence the detective analyzes, the better they become at identifying the relevant clues and making accurate deductions. Similarly, the algorithm iteratively adjusts its internal parameters to minimize the errors in its predictions. It's like fine-tuning a musical instrument. The more you adjust the strings, the closer you get to the perfect sound. The goal is to train the algorithm to a point where it can generalize well to unseen data. making accurate predictions even on examples it has never encountered before. This training process can be computationally intensive, especially with large data sets and complex algorithms. It's like solving a giant jigsaw puzzle. The more pieces and the more intricate the image, the longer it takes to put it together. But the end result is a trained model, ready to apply its learned knowledge to new, unseen data and make intelligent predictions. After all the hard work of training, it's time to put our model to the test. Just like a student facing an exam, the model must apply what it's learned to new situations. That's where the test set comes in, a portion of labeled data we set aside earlier. The model makes predictions and we compare them to the true labels. We use metrics like accuracy, precision, and recall to measure performance. It's like grading an exam. The better the score, the better the learning. This also helps us catch overfitting and ensure real-world reliability. One of the most common, and honestly, most successful applications of supervised learning is spam filtering. Every single day, billions of emails are flying around the world, and yeah, a huge chunk of them are just straight-up junk or spam. Spam filters, powered by supervised learning, help keep our inboxes clean and protect us from phishing attacks and other kinds of malicious stuff. So, how does it actually work? Well, spam filters are trained on massive data sets of labeled emails, each one marked as either spam or not spam. The algorithm then learns to spot patterns in the content like sender info, keywords, or even how the message is structured, that hint it might be spam. For instance, emails with phrases like guaranteed riches or urgent request are way more likely to be flagged as spam. And the best part? The filter keeps learning and adapting, getting smarter over time as it encounters new spam tactics. So, the next time you open your inbox and it's magically free of spam, you can thank a supervised learning algorithm for that. This seemingly simple tool is actually a great example of how powerful supervised learning can be in solving real-world problems and honestly just making our digital lives a bit easier. Imagine you're playing a game of 20 questions. You ask yes or no questions to narrow down the possibilities. That's exactly how decision trees work in machine learning. They ask a series of questions, each answer leading to a new branch. Say we want to predict if someone will like a movie based on age and genre. The tree might ask, is the person over 30? Then do they prefer action movies? Eventually, it predicts likely or unlikely to enjoy the movie. What's great is you can see how the model made its decision. And with pruning, we keep it simple and accurate. Pretty neat, right? Imagine moving to a new neighborhood. You'd probably observe your neighbors to figure out who's similar to you. That's basically how K-nearest neighbors, or KNN, works. K represents the number of closest data points the algorithm considers when making a prediction. It looks at the K most similar examples in the training set and assigns the new point to the majority class. For instance, to classify a new customer as a high or low spender, KNN checks the spending habits of similar customers and goes with the majority. It's simple, intuitive, and works well when decision boundaries are irregular. But it can be slow with large data sets, since it compares every new point to all existing ones. Despite the name, logistic regression is used for classification, not regression. It uses a sigmoid function to output probabilities between 0 and 1, perfect for predicting outcomes like loan approvals or ad clicks. For example, it can estimate a student's chance of passing an exam based on study hours and grades. Its ability to output probabilities makes it ideal for risk assessment and decision-making. Support vector machines, or SVMs, are great at drawing the best possible line or hyperplane that separates different classes. They maximize the margin between the closest data points from each class, called support vectors. For example, in classifying cat versus dog images, SVMs find the boundary that best separates the two. They're especially powerful with high-dimensional or non-linear data thanks to kernel tricks. Just like a carpenter picks the right tool, data scientists choose algorithms based on the problem and data. Factors like dataset size, task type, interpretability, and computational resources all matter. Decision trees offer clarity. KNN handles complex boundaries, logistic regression predicts probabilities, and SVMs find optimal separations. No one-size-fits-all. Understanding each algorithm's strengths is key. Sometimes combining multiple tools gives the best results. Supervised learning isn't just a lab experiment, it's transforming real life. From personalized recommendations to fraud detection, it's working behind the scenes to make life smoother and safer. In healthcare, it helps diagnose diseases early. In finance, it manages risk and detects fraud. In environmental science, it analyzes climate data to fight climate change. Let's explore some of these real-world applications. Supervised learning is revolutionizing healthcare, especially in medical imaging. Algorithms trained on X-rays and MRIs can detect patterns even doctors might miss. This leads to earlier, more accurate diagnoses of diseases like cancer and heart conditions. It's also used to personalize treatments based on genetics and lifestyle. Hospitals use it to predict readmissions and streamline operations. The potential for better, faster, and more personalized care is enormous. Ever wonder how Netflix or Spotify seems to know you so well? That's supervised learning at work. These systems analyze your past behavior to predict what you'll like next, be it music, movies, or products. For example, if you love jazz, it might suggest niche subgenres or similar artists. While it boosts engagement, it's also important to be aware of filter bubbles and echo chambers. In finance, supervised learning is a frontline defense against fraud. Algorithms scan massive transaction datasets to flag suspicious activity, like credit card fraud or money laundering. It's also used to assess credit risk, forecast markets, and automate services. As financial systems grow more complex, these tools become even more essential. Supervised learning is helping keep our money and our data safe. Supervised learning is expanding into new frontiers. In transportation, it powers self-driving cars, helping them interpret surroundings and make decisions. In education, it personalizes learning by adapting to each student's pace and style. These innovations promise safer roads and more equitable classrooms, and this is just the beginning. New applications are emerging every day. Supervised learning is powerful, but not without challenges. One major issue is bias. If the training data is biased, the model will be too. For example, facial recognition systems trained mostly on light-skinned faces may perform poorly on others. Another concern is job displacement, as automation replaces human roles. While new opportunities may arise, we must support workers through the transition. Ethics and accountability must guide how we use this technology. The future of supervised learning depends not just on innovation but on responsibility. Let's use it wisely for the benefit of all. Teaching a machine with labeled data is like training a dog with treats. It learns by example. Supervised learning excels when we have clear goals and lots of labeled data. It's great for tasks like image recognition, spam filtering, and medical diagnosis. Once trained, these models are fast and accurate, perfect for real-time applications. And with interpretable models like decision trees, we can understand how decisions are made. That builds trust, especially in critical fields like healthcare and finance. Supervised learning is powerful, precise, and often transparent. But supervised learning has its limits. It relies heavily on labeled data, which can be expensive and time-consuming to collect. In rare cases, like detecting uncommon diseases, there may not be enough data to train an effective model. These models also struggle with unfamiliar situations outside their training data. For example, a self-driving car trained in sunny weather might fail in snow. Overfitting is another issue. Models can memorize training data but fail to generalize. It's like a student who aces practice tests but flunks the real exam. So while supervised learning is powerful, it's not a one-size-fits-all solution. Imagine a student who memorizes every answer instead of understanding the concepts. Sure, they might ace the test, but their knowledge is shallow and fragile. Supervised learning models can fall into the same trap. It's called overfitting. The model learns the training data too well, even the noise and quirks. So it performs great on training data but fails on new unseen data. To fix this, we use regularization and cross-validation to reduce complexity. It's all about balance, teaching the model to find real patterns, not just memorize. Picture a mirror that reflects a distorted image. It might look accurate at first glance, but the flaws in the mirror warp what you actually see. Supervised learning models can do something similar. They can inherit and even amplify the biases that are baked into their training data, leading to outcomes that are unfair or even discriminatory. Data bias can creep in from all sorts of places. Maybe certain groups are underrepresented in the data, or maybe the way the data was collected was biased to begin with. Sometimes the data just reflects societal biases that already exist. For instance, take a facial recognition system that's trained mostly on light-skinned faces. That system might struggle to recognize darker-skinned faces, and that kind of failure can reinforce racial bias in real-world applications. And the consequences? They can be serious. Things like unfair loan approvals, biased hiring decisions, or even incorrect medical diagnoses. Tackling data bias isn't easy, but it's crucial. It means being thoughtful about how we collect and clean data, using techniques to reduce bias during training, and constantly monitoring how the model performs across different groups of people. At the end of the day, supervised learning models aren't magically objective. They're shaped by the data we feed them. And if we're not careful, they can end up reflecting, and even magnifying, the inequalities we already have in society. Imagine a child exploring a playground for the first time. No one's giving them step-by-step instructions. They're just observing, interacting, and learning through curiosity and discovery. That's kind of what unsupervised learning is like. It's a branch of machine learning where models work with unlabeled data, trying to uncover hidden patterns and relationships all on their own. Unlike supervised learning, where we basically hand the model the answers, unsupervised learning gives the model a lot more freedom to explore the data and draw its own conclusions. That makes it especially useful for things like clustering, where we group similar data points together, or anomaly detection, where we're looking for things that don't fit the usual pattern. For example, we might use an unsupervised algorithm to group customers with similar buying habits, spot fraudulent transactions that look out of place, or even find hidden patterns in gene sequences that could point to disease risk. Sure, unsupervised learning doesn't have the clear guidance of labeled data, but it opens up this powerful way to explore and understand data in a more open-ended, flexible way. It's like giving the machine a flashlight and letting it roam around, lighting up the hidden structures and relationships tucked away in the vast universe of data. Well, we've reached the end of our journey through the fascinating world of supervised learning, and it's time to reflect on just how far our student has come. We started with raw data, a jumble of numbers and pixels that, honestly, didn't mean much on their own. But through careful labeling, we transformed this data into a language the machine could actually understand, giving it the essential building blocks for learning. We introduced the machine to a diverse cast of algorithms, each with its own unique strengths and learning style. The decision tree, sort of like a wise sage, asked a series of questions, branching out to reach a prediction. The K-nearest neighbor, more of a social butterfly, looked to its closest peers for guidance. Then we had the logistic regression, a real master of probabilities, weighing the likelihood of different outcomes. And of course, the support vector machine, a precise architect, drawing boundaries to separate and classify. Through rigorous training, we helped the machine find patterns, make connections, and ultimately generalize from known examples to those it had never seen before. We tested its knowledge, pinpointed its weaknesses, and refined its understanding. And finally, like proud mentors, we've seen our student graduate, equipped with the knowledge and skills to take on real-world challenges. But this graduation is not the end, it's merely the beginning. Our student is now ready to step out into the world, not as a passive observer, but as an active participant, shaping industries, driving innovation, and influencing the very fabric of our lives. In healthcare, supervised learning is assisting doctors in making faster, more accurate diagnoses, paving the way for personalized medicine and potentially saving countless lives. In finance, it's bolstering security measures, detecting fraud, and helping manage risk in an increasingly complex financial landscape. And in our everyday lives, it's personalizing our online experiences, recommending products, filtering spam, and even powering the voice assistants we interact with daily. The impact of supervised learning is far-reaching, touching nearly every aspect of modern society. It's optimizing supply chains, improving energy efficiency, powering self-driving cars, and even aiding in the fight against climate change. As we feed the machine more data and refine its learning algorithms, its potential seems, well, pretty much limitless. However, amidst this technological revolution, it's crucial to remember that supervised learning is a tool, and like any tool, its impact depends on the hand that wields it. As we embrace the power of artificial intelligence, we must also acknowledge the importance of human oversight, ethical considerations, and responsible development. We must be vigilant in addressing potential biases in training data, ensuring that our machines learn to be fair and equitable in their decision-making. We must prioritize transparency and explainability, striving to understand the why behind the machine's predictions, especially in sensitive domains like healthcare and criminal justice. And we must engage in thoughtful discussions about the societal impact of artificial intelligence, addressing concerns about job displacement and ensuring that the benefits of this technology are shared by all. Supervised learning, for all its power, is not a replacement for human intelligence, but rather an extension of it. It's a tool for augmenting our capabilities, not abdicating our responsibilities. The future of intelligence is not about machines replacing humans, but about humans and machines working together, each complementing the other's strengths. We bring creativity, empathy, and a nuanced understanding of the world, while machines offer speed, scalability, and the ability to find patterns in vast amounts of data. Imagine a future where doctors, aided by AI-powered diagnostic tools, can focus on patient care and develop more effective treatment plans. Imagine a future where teachers, equipped with personalized learning platforms, can tailor their instruction to meet the unique needs of every student. Imagine a future where scientists, armed with AI-powered research tools, can accelerate discoveries and tackle some of humanity's greatest challenges. This is the promise of supervised learning, not as a replacement for human ingenuity, but as a catalyst for it, enabling us to reach new heights of knowledge, understanding, and innovation. Our exploration of supervised learning ends here, but the adventure of machine learning is far from over. Beyond the realm of labeled data lies a vast and uncharted territory of unsupervised and reinforcement learning, each with its own unique challenges and opportunities. So keep asking questions, keep exploring, keep learning. The world of machine learning is vast and ever-evolving, and it's waiting for curious minds like yours to unlock its secrets. Who knows what groundbreaking discoveries and world-changing innovations await on the horizon? The only way to find out is to keep exploring, keep learning, and keep pushing the boundaries of what's possible.